Welcome back, everyone. Today we're going to look at 5.9 and 5.10. So for the doing that today, imagine you have an empty plastic bottle that's kind of corked. What happens if you step on it? Explain what happens in terms of pressure and volume. Alright, so if you have your notes out, this is 3.9 and 3.10, which really gets at what pressure is, as well as Boyle's law. So pressure. We talked about what temperature was, so remind yourselves, what is temperature? What do we mean when we say pressure? So think about it. Pressure is kind of, gases do exert pressure, just like gases have mass. There is pressure. You can kind of think of it as, if I fill a balloon with gas, somehow it stays large, right? Something is bouncing off the inside of that balloon to keep it in this nice round shape that doesn't just deflate immediately. So pressure is defined in physics and always as force per unit area. So how much force you're putting on an area. So imagine poking a pencil at your hand. That's a good amount of force in a pretty small area because it's the tip of the pencil that's poking your palm. On the other hand, if you had like the back end of a highlighter, a big circle, that's more area with the same force, but it's less pressure. So it turns out gas molecules can exert pressure as well, and this happens as the molecules hit the walls of whatever container it's in. That's how you kind of can envision pressure in terms of gases. We measure pressure in a lot of different ways. Just like temperature has 3 different scales that we can measure it on: Fahrenheit, Celsius, Kelvin. Pressure also has a ton. But the most common ones we'll talk about are probably atmospheres. So an atmosphere is literally how much pressure is caused by all the air that's on top of you all the time. We don't feel it explicitly, just like we don't feel, the motion of the earth or something. We're just used to it. That's the normal. But that's the pressure that you would have at sea level, just 1 atmosphere, which is the same thing as 760 millimeters of mercury. This kind of comes from the way they used to build barometers, which measure pressure. They kind of see how high a column of mercury rises, so it's a kind of historical thing. And all of that is also equal to, sorry, that's not written right, 101,325 pascals, PA, not kilopascals. Let me fix that right now, just pascals. And so these are all conversion factors. You could convert between them if you needed to, but that shouldn't be necessary most of the time. So again, atmospheres, millimeters of mercury, pascals. If you're not really familiar with the unit, it's probably pressure. And Boyle's law relates pressure to volume. So if we look at this graphic on the right, we can see in the container on the left, there's more space, more volume, and less pressure. But if you kind of squish the lid down, the volume goes down, there's less space for the gas molecules, and pressure goes up. Because in a smaller space, the particles bump into walls more often, and that kind of increases the force. And then the pressure in that container is also said to go up. So basically, gas pressure and volume are inversely related. When one goes up, the other goes down. Unlike in Charles's law, we saw that volume and temperature were directly related. They go the same direction. These are opposite from each other. So this is expressed mathematically as P1V1 equals P2V2. We've kind of seen similar things before. We've seen it like in a dilution type setup. We had this proportionality as well. But this is the formula you'll be using to solve problems that want to relate pressure with volume. So now we've kind of talked a little bit about these 3 quantities we always measure with gases. Temperature, which is the kinetic energy of particles, and again, kinetic energy is dependent on mass and velocity, how fast they're going. That's what temperature measures, and we can measure it using any of these 3 units. So that's just a standard temperature reading. Volume is how much space something takes up. This was back from when we learned density, way back in alchemy. But oftentimes in liters. You could also do cubic meters, cubic centimeters, etc. So how much volume does a balloon take up, or a bottle, or a basketball, anything filled with a gas. And finally, pressure, which is how much the particles are running into the walls of the container, measured in these new weird units. And again, the atmospheric pressure at sea level is 1 atmosphere. Sometimes a problem will tell you that the gas starts at, quote, STP. STP, and you should write this down somewhere, stands for standard temperature and pressure, and it means the same thing everywhere. So whenever doing experiments with gases, chemists must make sure that you have the actual same amount, because gases do different things at different conditions. So this is a standard around the world, and STP is defined to be 1 atmosphere and 0 degrees Celsius. All right, like last time, here's a practice problem. So pause, try it out yourself. All right, so as before, we have a new problem, and I see that the variables involved are a volume in liters and a pressure in atmospheres. So it's probably Boyle's law that we care about here. So P1 V1 equals P2 V2. And I can see that my starting volume is 7.5 liters. And my starting pressure is 1 atmosphere. Again, since these are proportions, it doesn't really matter what the unit is as long as it's the same on both sides. And then my final volume is known. My pressure is not. What happens to the pressure? P is unknown, P2 times 2.5 liters. And before even solving for it, if you go underwater, you might know that there's more pressure there. The pressure should go up because the volume went down. It's kind of like the balloon got squeezed to a smaller volume while keeping all of the molecules that were inside of it. So it would probably have a higher pressure. So when I do the math here, I should get 3 atmospheres equals P2. So the pressure should increase, and it increases actually to a pressure of 3 atmospheres. That might be enough pressure actually to just pop the balloon, but you don't actually know whether or not it pops in this problem. All right, you guys are definitely welcome to work on the workbook problems or finish up simulation 2 at this point.